The question I have is, could you explain the projection method of resolving a 3D force vector into components? When you go from 2D to 3D, finding the components of a vector becomes a little bit more involved. There are at least three different methods of doing this: the projection method, the direction angle method, and the position vector method. In this video, we'll discuss the first method, the projection method. But before we do anything, let's talk about how to define a three-dimensional Cartesian coordinate system. The system consists of three perpendicular axes. Let's call them as x, y, z. The question is the definition of them kind of arbitrary, or is there a specific way in which they are defined? The answer is the latter. There is a specific way in which you define the positive directions of x, y, and z axes. So this is how you do it. You use the right-hand rule as illustrated in this picture right here. Once you select your x and y axes, you hold your right hand like shown in this picture. Your fingers should curl up like you are taking the x-axis and rotating it towards the y-axis. Then your thumb tells you the direction of the z-axis. For example, consider the system in this first picture. Your fingers should curl up from x to y axis. That means should be in the counterclockwise direction like shown here, right? Your thumb is then going to be like this, like coming out of the paper, plane of the paper, right? The z-axis should be in that direction, and therefore this is the correct way to define the z-axis. And therefore this is the wrong way to define the z-axis. Next, let's talk about what exactly are the components of a three-dimensional vector. Let's say we have a 3D vector, little a, which goes from the origin of this three-dimensional Cartesian coordinate system to this point right there. Let's draw a little cuboid around it, such that the vector a becomes one of the diagonals of the cuboid, like shown in this picture. A cuboid is basically a three-dimensional rectangular box, if you will, right? So these four lines are parallel to the y-axis, and these four lines are parallel to the x-axis, and these four lines are parallel to the z-axis, right? Then the dimension of this box in the x direction, which is this much right here, is the x component of this vector. Similarly, the dimension in the y direction is ay, and the z direction is az. Now let's talk about the projection method. Supposing, say, these two angles, alpha and beta, are given. In addition to that, of course, the magnitude of A is given. So this is what we do. Well, first, I want you to convince yourself that the lines AB and CB are perpendicular to each other. The line CB is on the top face of this box, and the top face is parallel to the XZ plane, right? But the line AB is perpendicular to that plane, and therefore any line on this horizontal plane, the XZ plane, is going to be perpendicular to the line AB, and ZB is one of those lines, and therefore these two are perpendicular to each other. Now I'm going to consider this right triangle ABC. The line AC is the hypotenuse of that triangle, right? Let's use trigonometry to find the other two sides, AB and BC. So AB is basically A, which is the magnitude of little a, cosine alpha, right? BC is A sine alpha, right? For this angle alpha, AB is the adjacent side, BC is the opposite side, right? We immediately know two things. One, AB is simply little ay. That's the y component of A. Second thing we know is that because this is a rectangular box, BC and AD are equal to each other. Now we're going to come down to this plane, the XZ plane, and consider this triangle, AED. We note that this line right here, ED, is perpendicular to the z-axis, right? So this triangle, ADE, is also a right triangle, and we know this angle, right, beta, which is given. And AD becomes the hypotenuse of that triangle, and therefore we can find these two sides, AE and ED. DE equals AD sine beta, and AE equals AD cosine beta, right? We already found AD here, and now substituting that expression for AD, we have this for DE and this for AE. At this point, we know that DE is simply equals AX and AE simply equals AZ. So we found the three components, AX, AY, and AZ. Vector A can now be written in its component form like this. So this is the essence of the projection method. So you can basically see that this method involves two levels of projection. First you project it to get AB and BC. Then we note that BC is equal to AD. Now we project it one more time in order to get AE and ED. At this point we have the three components. In some problems, some of these angles could be such that some of these components will be negative. So you want to understand the problem at hand and do it accordingly. So don't memorize any of these formulas. Just understand the method. Then you can apply to the problem at hand.